So in this video, I'll discuss the concept of chemical equilibrium and some techniques on the calculation of equilibrium concentrations. Okay, so chemical equilibrium is an equilibrium state where number one, the number of components in the system is constant. So hindi nagkakaroon ng bagong component, hindi rin tayo nawawalan ng components. So kung halimbawa 4 yung components doon sa system at equilibrium, mananatili siyang 4 components. Okay, hindi siya nagiging 5 or 3. So also, yung amounts ng mga components na yon ay hindi nagbabago. So that's chemical equilibrium. The number of components and the amounts of each components in the system is constant for a given period of time and certain states. So at constant temperature and pressure to, of course, kasi we are dealing with chemical processes na constant ang temperature and pressure. Okay? So statement 1 can be interpreted in two ways. So if the system is at equilibrium, pwede nating i-interpret na static yung system, wala nang reaction na nangyayari. So, wala nang processes na nangyayari na kahit hindi natin napapansin, okay, we are assuming that the system is static. Okay? Walang natatransform into reactants, wala rin natatransform into products. So, the reaction basically stops. So, pwede rin nating sabihin na the system is dynamic. Pwedeng nagkakaroon pa rin ng transformation from products to reactants and reactants to products, pero yung rate of formation ng products, okay, or yung rate of forward reaction ay equal lang sa rate ng backward reaction. So kung gaano kabilis nako-consume yung products, ganun din kabilis siya na-form. Okay? So yun yung ibig sabihin ng dynamic na system. So kapag static yung system, wala talagang nangyayari. Okay? Hindi ka nagkakaroon ng transformation whatsoever. Pero kapag ka dynamic, okay, ang system mo ay merong reactions pero hindi natin apparently napapansin. Okay? So, paano natin i-establish yung equilibrium state? So, if we have a reaction kung saan initially meron lang tayong reactants at may kakaunti tayong products or minsan wala tayong products, okay? So, if we let the reaction happen, magkakaroon tayo initially ng rate of disappearance of reactants. So, mapapansin natin na nagbabago yung concentration ng reactants, lumiliit siya. Yung reactants na yon ay nagiging products, kaya yung rate of formation ng ating products ay nag-i-increase. So, that's a change in the concentration per change in time. Okay? So yung rate nila mapapansin nyo dahil nagkakaroon tayo ng mga physical changes or mga chemical changes doon sa ating system. Okay? So merong time na hindi na natin mapapansin yung rate of disappearance or formation ng reactants and products natin. So kapag ganyan ay nangyari, ibig sabihin yung system nyo ay nasa equilibrium na. Okay? So kapag nasa equilibrium na, pwede na natin siyang i-interpret in two ways. Again, we have the static interpretation wherein wala talagang reaction na nangyayari. Okay? So hindi nagiging products yung reactants, yung products hindi na nagiging reactants, and wala na talagang reaction na nag-occur. Okay? Pero kapag dynamic, pwedeng hindi natin napapansin yung changes, pero yung products nyo nagiging reactants and yung reactants nagiging products din. Pero yung rate of the formation or disappearance ng products ay equal din sa rate of formation or disappearance ng ating reactants. Kaya wala tayong net change. Okay? So, we also have two definitions of chemical equilibrium. So, sa thermodynamics, the delta G of the state is zero at constant temperature and pressure. So, kapag zero yung delta G ng reaction nyo, ibig sabihin, yung reaction nyo ay nasa state of equilibrium or chemical equilibrium. Okay? So, chemical kinetics naman, it interprets rates. So, the rate of the forward reaction or yung speed ng forward reaction is equal to the speed or the rate of the backward reaction. That is the kinetic definition of your chemical equilibrium. So, pwede natin siyang i-interpret in any way we want to, pero pareho pa rin naman silang tama. Okay? So, in this part, we will derive the equilibrium constant. Okay? So, yung equilibrium constant, ginagamit siya para ma-assess natin kung yung system ay nasa equilibrium na. Malalaman natin yung relative amounts ng reactants and products given their initial conditions. Ginagamit din yun pang predict, kumbaga, ng magiging equilibrium concentrations ng ating reactants and products sa isang reaction. Okay? So, let's consider this reaction at constant temperature and pressure. So, A plus B produces C plus D. So, yung A, B, C, and D are coefficients of the balanced reaction. Okay? So, the delta G of the reaction of the forward reaction, so yung forward reaction na to, okay, or yung reaction symbolized by the forward arrow, so that's from A plus B to C plus D. Okay? It can be expressed as the delta G of the reaction is equal to the delta G of the products minus the delta G of the reactants. So, state function din ang delta G. Para siyang delta H and delta U. So, para makuha natin yung delta G ng reaction, we will have to subtract the delta G of the reactants from the delta G of the products kapag forward yung process. Okay? So, this is the delta G. So if the delta G of the reactants is greater than that of the delta G of the products, the forward delta G is less than 0. So ibig sabihin, it will favor the forward step kasi spontaneous or mas spontaneous yung forward na reaction kaysa sa backward reaction. So if the delta G of the reactants is less than that of the delta G of the products, positive yung magiging delta G natin, so mas favored yung backward step. So yung forward step non-spontaneous kasi positive yung delta G niya, so yung backward step yung mas favored. Okay, thermodynamically. So if the delta G of the reactants is equal to the delta G of the products, the delta G of the reaction is 0. So ibig sabihin, the system is already at equilibrium given their amounts. Okay? So at constant temperature and pressure, the delta G of species I, or yung A or B or C or D natin, can be determined using the equation. So the delta G of species I is equal to the standard delta G of species I. So yung standard delta G, that's the delta G of the component itself, yung hindi pa siya involved sa reaction. Okay? So plus Ni RT times the Ln of the pressure of component I. Okay? So gases naman sila, as we can see here. Okay? Gases silang lahat. So, pwede natin gamitin yung pressure as a parameter. Or madali natin ma-determine yung pressure using the ideal gas equation. Okay? So, the molar delta G, also known as the chemical potential mu, can be determined if we divide both sides by n. So, kapag ginawa nyo na tong expression na to, okay, so magiging mu na siya kapag dinivide nyo yung delta G sa Ni. So, itong Ni na to, i-divide nyo lang siya sa both sides para makuha nyo yung mu. So, mu I is equal to the standard mu of component I plus RT times Ln of the pressure of component I. So, meron na tayong ganitong equation. Okay? So, we will use this expression, okay, or equation to determine the standard chemical potential of the reaction and the chemical potential of the reaction at specific conditions. Okay? So, iba yung standard mu I sa mu I ng reaction at specific conditions. Okay? So, the molar delta G is the chemical potential. Okay? So, kapag sinubstitute natin yung mga component parameters, we will have the mu of A, the mu of B, the mu of C, and the mu of D. Okay? So, that would be corresponding to mu naught of A, or the standard chemical potential of A, plus RT times the Ln of the pressure of component A. Plus, okay, or for component B, the mu of B is equal to the mu naught of B plus RT Ln P of B. Okay? So, ganun din sa C, we will use the pressure of C. Tapos sa D, we will use the pressure of D. So, meron na tayong 4 na equations. Makukuha na natin yung delta G ng reaction or yung mu ng reaction using these 4 equations. Okay? So, therefore, the chemical potential of the reaction is equal to the chemical potential or sum of the chemical potentials of the products minus the sum of the chemical potentials of the reactants. Siyempre, multiplied yan by their corresponding stoichiometric coefficients. So, the mu of the reaction is equal to the mu, sum of the mu of the products minus the sum of the mu of the reactants, multiplied, of course, by their respective stoichiometric coefficients. So, kapag sinubstitute nyo, you will just have to multiply them by their respective coefficients, tapos makukuha nyo na yung buong equation. Okay? So, that would be the equation for the chemical potential of the reaction. Okay? So, after sorting out similar terms, we will get this equation. So, the mu of the reaction is equal to D times the standard mu of D plus C times the standard mu of C minus B times standard mu of B minus A times the standard mu of A plus RT times D Ln pressure of D C plus C Ln pressure of C minus A times the Ln of pressure of A minus B times Ln pressure of B. So, i-operate natin itong mga rules on logarithm dito sa expression enclosed by the parenthesis. So, kapag nakamultiply dun sa Ln, we can use it or transpose it to become an exponent. Tapos, kapag addition between Ln, okay, so Ln y plus Ln x, pwede siyang maging Ln of x times y. So, kapag naman subtraction, so Ln y minus Ln x, magiging division siya. Okay, so Ln of y over x. So, kapag in-apply natin yung rules na yan dito sa expression na to, we will get this one. Okay? So, that's plus RT Ln P of C raised to C times P of D raised to D over P of A raised to A times P of B raised to B. Okay? So, yan na ngayon yung tinatawag nating reaction quotient or Q. Okay? So, the reaction quotient is the one that relates the relative pressures of the products and the reactants in a specific state. So, not necessarily an equilibrium state kasi we may have a value of the mu of the reaction. Okay? So, we can transform this equation into this one. So mu of the reaction is equal to the standard mu of the reaction. So this is the standard mu. So the difference between the sum of the mu of the products, okay, and the mu of the reactants. So ito na yung standard mu or the standard chemical potential of the reaction plus RT times ln of the reaction quotient, which is Q. Okay? So at equilibrium, we will set this one to 0. So dapat ito ay maging 0. Okay? So the mu of the reaction is 0 at equilibrium. Therefore, the standard chemical potential of the reaction is equal to negative RT times ln of KEQ. Kasi isa lang naman ang value ng KEQ at this condition kapag 0 yung mu ng reaction. Okay? Unique ang value niya kapag 0 yung mu ng reaction depending dun sa type ng inyong system. Okay? So, the Q is now equal to the KEQ. So, the KEQ is a value that can be obtained kapag isa-set mo yung mu ng reaction sa 0. Ibig sabihin yung system mo ay nasa equilibrium na. Okay? So, some notes, if the Q is greater than the KEQ, ibig sabihin at any point in the reaction, if the reaction quotient is greater than KEQ, the reaction favors the backward step. Ibig sabihin, there are too many products in the reaction. So, mas mataas yung value ng numerator kaysa sa denominator. Okay? Kapag naman, the Q is less than the KEQ, the reaction favors the forward step. Ibig sabihin, masyado namang maraming reactants. So, dapat mag-increase yung value ng Q para maging equal na siya sa KEQ. Okay? So, now we have derived the equilibrium constant or KEQ. So, again, the mu of the reaction is equal to the standard mu of the reaction plus RT ln Q. Okay? So, Q kapag ka any point before or after the equilibrium. So, in between states yan. So, yan yung mga pwedeng initial or values in between ng mga concentrations ng inyong mga components doon sa system. So, kapag ka 0 na yung delta G ng reaction or yung inyong chemical potential, the lnQ becomes lnKEQ. So, it becomes, okay, mu naught reaction is equal to negative RT ln KEQ. So, the Q becomes KEQ kapag ka equilibrium na yung system nyo. Okay? So, yung mga amounts din ng reactants and products nyo, they are already at their equilibrium amounts. Okay? Pwedeng in terms of pressure or concentration. Okay? So, we can also convert the pressure KEQ or K sub P to concentration KEQ or K sub C. So, we can use the ideal gas equation para ma-derive natin yung relationship. Kasi, yung mga gases naman natin doon ay assumed to be ideal. Okay? So, using the ideal gas equation, PV is equal to nRT, we can relate P. Okay? So, P is equal to N over V times RT. So, N over V is the concentration. So, number of moles of component over the volume of the system. So, that's also P equals C RT, or pwede natin gamitin yung bracket RT as long as may component dun sa loob ng bracket. For example, A. Okay? So, let's consider the same reaction na ginamit natin kanina. So, from that reaction, we have derived Kp. So, this is the expression for Kp. So, isa-substitute lang natin yung bracket RT doon sa pressures. So, magkakaroon tayo ng ganitong expression. Okay? So, pwede natin i-isolate dyan yung RT. So, magiging, okay, ganito yung value ng RT natin. Kasi, that becomes RT, the A or C plus D over RT. So, the A plus B. So, meron tayong rules of exponents. Okay? So, x to the m times x to the n is equal to x to the m plus n. Kaya ganito yung nangyari dun sa taas. Okay? So, kapag x to the m over x to the n, that becomes x to the m minus n. So, from here, magiging ganito siya. Okay? So, C plus D minus A minus B is the difference between the number of moles of gases between the products and the reactants. Okay? So, ito yung moles of gases sa products, ito yung moles of gases sa reactants doon sa ating balanced reaction. So, basically, it's delta Ng. Okay? So, the delta Ng is the difference between the number of moles of gases between the products and the reactants. Okay? So, for the concentrations, it's basically C raised to C times D raised to D over A raised to A times B raised to B. Kaya ganito na. So, ito na ngayon yung ating K sub C. Okay? So, therefore, Kp is equal to Kc times quantity RT raised to delta Ng. So, that's how you relate the pressure equilibrium constant to the concentration equilibrium constant. Okay? So, how do we write equilibrium constants? So, first, the species that are included in the equilibrium constant are those usually within the same phase. So for example, sa mga gases, kung ano lang yung nandun sa loob ng container at kung ano lang yung nag-interact within that system, yun lang yung included dun sa ating equilibrium constant. Pero kapag may inert gases na hindi nagpa-participate doon sa reaction, hindi natin siya isasama sa KEQ. Okay? For solids and solvents, okay, hindi siya kasama sa equilibrium constant kasi yung solids and solvents hindi nagbabago yung concentration nila with respect to their own phases. Okay? So, for example, hindi nagbabago yung density ng solid kahit bawasan mo siya or dagdagan mo siya ng amount. Okay? So, constant lang basically yung concentration ng solid within its own phase. So, ganoon din ang solvents. Okay? Kahit bawasan, dagdagan mo yung solvents na same pa rin yung magiging density niya at constant temperature. So, hindi basically nagbabago yung kanyang concentration. Okay? So, for example, if you dissolve sodium bicarbonate, okay? So, yung sodium bicarbonate, nadi-dissolve siya sa water, so nagpo-produce siya ng Na+, plus the bicarbonate anion. So, single arrow lang to kasi sodium bicarbonate is very soluble sa tubig. Okay? So, that is the dissolution of solid sodium bicarbonate in water. Okay? So, yung bicarbonate, it further interacts with water to produce the carbonate anion and H3O+. So, yung hydrogen plus ng bicarbonate ay magko-combine dun sa water. Okay? So, this is an acid-base reaction between the carbonate and water. So, yun yung interaction. So, makikita natin nagpa-participate naman yung water doon sa ating system, pero hindi natin siya isasama sa KEQ. Okay? Kasi ang solvent nito ay water. So, kahit mabawasan yung amount ng water, same pa din yung concentration niya. So, hindi siya nakaka-apekto doon sa ating equilibrium constant. So, ang important lang dito ay yung carbonate, yung H3O+, kasi that's a species that forms kapag nandun yung ating bicarbonate. Okay? So, ito yung KEQ natin. So, products over reactants. So, that's CO3 2- concentration times H3O+ concentration over the bicarbonate concentration. So, that's the KEQ expression for this reaction. So, dito, hindi natin kailangang i-determine yung KEQ dahil basically kung ano yung amount ng sodium bicarbonate na solid na i-dissolve sa water, yun din yung magiging amount ng Na+ and HCO3- na mapupunta dun sa solution kasi siya ay very soluble. So, no need to determine the equilibrium constant here. Okay? So, why is water not in the KEQ expression in NQ systems? So, it is actually included naman. Pero, naka-incorporate na siya dun sa KEQ. Okay? Kasi hindi siya nag-increase or nagde-decrease ng concentration at any point in time between states. Okay? So, from initial to final, hindi siya nagbabago ng concentration. So, for example, let's illustrate kung paano hindi nagbabago yung concentration. So, calculate the concentrations of water in 100 grams and 10 grams water. So, let's assume that the density of water is 1 gram per ml. So, the molarity of water na 100 grams is equal to the number of moles of water. So, i-convert natin yung mass to number of moles by dividing 18.016 doon sa ating 100 grams over the volume of your solution or yung water. So, ang lalabas dyan ay 55.506 molar H2O. So, kapag naman 10 grams yung water, again, ganun pa rin ang gagawin mo. Okay? So, i-convert mo yung 10 grams to number of moles. So, magiging NH2O to over the volume of 10 grams water. So, ang lalabas pa rin dyan ay 55.506 molar H2O. So, kahit nagbabago yung amount niya, hindi nagbabago yung concentration niya. Okay? So, hindi natin siya kailangang i-include doon sa ating equilibrium constant expression. So, therefore, it is actually implied in the KEQ. Implied na siya. Okay? So, hindi natin siya kailangang i-include doon sa KEQ kasi nandun na siya naka-incorporate sa mismong value ng inyong equilibrium constant. Okay? So, parang ganito. So, if this is the KEQ, so the KEQ is also equal to some value of KEQ prime times the concentration of liquid water. Okay? So, kaya hindi na sinasama yung solvents and solids sa equilibrium constant expression kasi constant din ang value niya. Okay? So, here we have some examples of equilibrium reactions and yung kanilang equilibrium constant expressions. So, for example, we have the gas phase combination reaction of nitric oxide. So, 2NO2 na gas, naging N2O4 na gas. So, since pareho silang gases, the Kc, okay, so kung given ang volume, you can determine the equilibrium constant in terms of the concentration. That's the concentration of N2O4 over the concentration of NO2 squared kasi 2 yung coefficient na dito. So kapag in terms of pressure, that's pressure of N2O4 over the square of the pressure of NO2. Okay? So for the dissolution of carbon dioxide, yung gaseous carbon dioxide, okay, maghahalo siya sa water to produce carbonic acid. So the KEQ expression will exclude this water. So ang mangyayari, that's just the concentration of H2CO3 over the concentration of CO2 in solution. Okay? So next, we have the dissolution of carbonic acid. So carbonic acid plus water. So magdodonate siya ng proton, magiging bicarbonate plus H3O+. Again, hindi na included yung water sa KEQ expression. Okay, so that's bicarbonate concentration times yung H3O+ concentration over the carbonic acid concentration. Okay, so next, partial dissolution of AgCl in water. So AgCl is a solid, so hindi siya isasama dun sa ating KEQ expression. It produces Ag+ and chloride in solution. So the KEQ is just Ag+ concentration times the chloride concentration. Okay, so we have here the formation of a metal complex. So yung Ag+ nyo pwede mag-combine sa 2 moles ng ammonia to produce the diamine silver complex. So since aqueous sila lahat, so kasama sila doon sa system, so lahat sila ay in solution, pare-pareho silang nasa isang phase. So kasama lahat ng species sa KEQ expression. So that's a concentration of diamine silver over the concentration of Ag+ times the concentration of ammonia squared kasi 2 yung kanya coefficient. Okay? So sometimes makakita kayo ng mga equilibrium reactions written in a different way. So for example, okay, yung ating acetic acid, pag nag-combine siya sa water, magpo-produce siya ng acetate in solution plus H3O+. So ganito yung kanyang magiging KEQ expression. Okay, excluded yung water. So pwede nyo ring ipakita yung acetic acid na nag-dissociate lang into acetate and H+, so excluded dito yung solvent ng water, so hindi natin sinama sa reaction. Pero it is implied na nasa water yung ating system kasi because of the states, they are in aqueous solution. So that's the KEQ. So that's H+ concentration times acetate concentration over the concentration of acetic acid. Okay? So these are sometimes called net ionic reactions. So pwedeng ito yung net ionic reaction, okay? Pwedeng ito. Okay? So, kapag ka net ionic reaction, hindi na included doon yung mga tinatawag nating spectator ions. So, what are spectator ions? These are ions that do not affect the outcome of an equilibrium state kahit sila ay kasama sa starting materials natin or sa ating species. Okay? These are ions that are often excluded from the chemical reaction kasi hindi naman nagbabago yung concentration nila dun sa system. So for example, we have sodium+, K+, Cl-, Br-, and NO3-. So kapag ka sa equilibrium constant, okay, hindi na sila sinasama or kahit sa mismong chemical reaction dahil constant lang yung magiging amount nila dun sa solution. Hindi sila nagtatransform into another compound or another species dun sa solution. Okay? So malalaman natin kung bakit. Kasi they are very soluble in water. So hindi na talaga sila nag-interact kapag nasa water na sila. They are very stable ions in water. So for example, we have sodium carbonate. So pag hinalo nyo siya sa water, nagpo-produce siya ng bicarbonate plus the hydroxide ion plus 2Na+. So, tinatanggal na natin yung Na+ dito at dito. So, imbes na sodium carbonate yung ilagay natin, carbonate and ion na lang ilalagay natin. This is the net ionic reaction. So, carbonate plus water. So, kailangan pa rin natin i-add yung water kasi nag-i-interact yung carbonate sa water to produce the bicarbonate and the hydroxide. So, this is the KEQ. So, papansin nyo, wala yung sodium dun sa KEQ expression. So, ganun din dito sa sodium acetate plus water produces acetic acid plus Na plus hydroxide. So, wala na yung Na plus. Okay, tatanggalin natin yan kasi yan ay spectator ion. So, mangyayari, that's acetate plus water produces acetic acid plus the hydroxide ion in solution. So, this is the KEQ that we need. So, wala na dyan yung sodium plus. Okay? So, now let's proceed to the types of chemical equilibria. So, for the first type, we have the gas phase equilibrium. So, in this equilibrium, all components are gases. So, the KQ expression is usually expressed in terms of the pressure. So, Kp yung ginagamit kapag nag-express tayo ng equilibrium between gases. Okay? So, the Kp value is directly related to delta G given by this equation. Okay? So, mu naught is equal to negative RT ln KEQ. So, kapag given kayo ng standard delta G ng reaction, makakalculate nyo na yung equilibrium constant. So, for example, we have 2SO2 na gas plus the oxygen gas produces 2 moles of SO3 gas. So, Kp for this reaction is the pressure of SO3 squared over the square of the pressure of SO2 times the pressure of oxygen. So, lahat sila gases, so lahat sila included dun sa ating KEQ expression. Okay? So, for the next type, we have the solution equilibrium. So, these are for components that are interacting within a solvent phase. So, usually yung solvent natin ay water. Okay? So, for the first subtype, we have the acid-base equilibrium. So for acid-base equilibrium, this is for interaction of acids and or bases in solution. So for example, we have the dissociation of acetic acid in water. So that's acetic acid dissolved in water produces acetate, an ion, plus the hydronium cation. So this is hydronium. Okay? So the KEQ is usually expressed as the acid dissociation constant, or Ka. So Ka is equal to the concentration of acetate times the concentration of H3O plus over the concentration of acetic acid at equilibrium. So another type is, or another example is this. So ammonia dissolves in water to produce the ammonium cation plus the hydroxide anion. So the KQ is expressed as Kb. So Kb is equal to the concentration of NH4 plus times the concentration of hydroxide over the concentration of ammonia at equilibrium. Okay? So for the next type, we have the solubility equilibrium. So this is for partially dissolving salts in water. So for example, we have the silver chloride dissolves in water to produce the Ag plus cation plus the chloride anion. So in this case, yung chloride ay hindi spectator ion kasi naapektuhan yung concentration niya nung concentration din ng Ag plus. Okay? So nagbabago yung concentration niya. Kapag nagbabago yung concentration ng Ag plus, therefore, it is actually participating in reaction. So, sa ibang cases lang wherein the salt is very soluble, like sodium chloride, hindi natin kailangan ng Cl- or Na plus dun sa ating system. Or at least dito sa ating KEQ expression. Pero sa case na to, since hindi masyadong soluble yung AgCl sa ating solvent, we need the Cl- in the expression. So, KEQ is usually expressed as KSP. So, this is the solubility product constant. Okay, so the solubility product constant is the KEQ for this case. So that's equal to the concentration of Ag plus times the concentration of Cl minus in solution at equilibrium. So for the next example, we have the lead chloride. Again, yung chloride dito ay hindi spectator ion. So it produces Pb2 plus and 2 moles of Cl minus in solution. So the KSP is equal to the concentration of Pb2 plus times the square of the concentration of chloride in solution at equilibrium. Okay? So under the solubility equilibrium, we have the hydrolysis. Okay? So hydrolysis reactions happen after your salt dissolves in water. Yung mga dissolved ions nyo, mag-i-interact pa siya further with water to produce other species. Okay? So for example, yung inyong ammonium acetate, magpo-produce muna siya ng NH4 plus or ammonium ion, saka yung inyong acetate anion sa solution. So this dissolution is one-sided kasi very soluble ang ammonium acetate sa water. So yung ammonium nyo, magre-react pa siya sa water to produce ammonia plus H3O+. So this is the hydrolysis constant. So ang KEQ nito ay KH or the hydrolysis constant. Okay? So kapag hydrolysis, okay, meron tayong equilibrium between the ammonia and the ammonium cation in solution. Tapos may participation ng water at H3O+. Although hindi kasama again yung water sa ating expression. So yung acetate nyo, mag-i-interact din siya with water to produce the acetic acid plus the hydroxide, another hydrolysis constant for this reaction. Okay? So that's hydrolysis. After ma-dissolve ng inyong species sa water, mag-i-interact pa yung ions niya doon sa water to produce other species. Okay? So for this last one, we have the complexation equilibrium. So this equilibrium is pertaining to the formation of the metal complex in a aqueous solution. So for example, yung inyong Ag+, okay, mag-interact siya with ammonia to produce the amine silver complex. So the KEQ there is the formation constant. Ito yung expression ng KEQ kapag complexation equilibrium. So makikita nyo dito, that's the concentration of the amine silver and divided by the concentration of the Ag+ times the concentration of ammonia at equilibrium. So, meron din tayong combination ng copper at 6 water molecules to produce the hexa-aqua copper. Okay, so hexa-aqua copper 2. So, for this one, we have the concentration of the hexa-aqua copper 2 over the concentration of the copper 2 plus. So, pansin nyo, hindi ko na nilalagyan ng bracket kasi magkakaroon ng excess number of brackets dun sa ating equilibrium constant expression. So, pwede nyo gawin yon, okay, kapag dito sa pag-express ng ating equilibrium constant ng ating mga complex ions. Okay? So now let's discuss some properties of the equilibrium constant or yung equilibrium in general. Okay? So first, let's state the Le Chatelier's principle. So it states that when a stress is applied to a system at equilibrium, so kapag nasa isang equilibrium state yung system at nag-apply ka ng stress, okay, the system approaches a new state to adapt to the stress. So pwede siyang mag-shift forward or shift backward depende dun sa in-apply niyong stress. Okay? So ano yung mga example ng stresses na pwede nating i-apply sa system na nasa equilibrium? So first, we can apply changes in the temperature. Okay? So kapag nag-apply tayo ng increase or decrease in the temperature, the KEQ value changes. Okay? Yung value ng mismong KEQ nagbabago siya. So paano siya nagbabago? So we have here the delta H, okay, pwede siyang endothermic or exothermic. Yung change ng temperature natin doon sa system, pwede lang i-increase or i-decrease yung temperature and yung effect niya sa equilibrium. Okay? So kapag endothermic, it means that for a reaction A in equilibrium with B, nasa reactant side yung ating delta H or yung heat. Okay? Yan yung mga endothermic reaction. So kapag in-increase mo yung temperature, ibig sabihin yung delta T is greater than 0, mas mataas yung final kaysa sa initial, okay? The system will shift its equilibrium forward. So magi-increase yung value ng KEQ nyo. Okay? So kapag endothermic at increase ang temperature, magfo-forward yung inyong equilibrium shift. So kapag naman din-increase mo yung temperature, kabaliktaran lang yung mangyayari. Bababa yung KEQ, magba-backward yung shift natin ng equilibrium. So kapag forward, from A to B, pag backward, B to A. Okay? So, yan yung effect kapag sa endothermic processes. Paano naman kapag sa exothermic processes? So, kapag exothermic, nasa product side, yung ating delta H. Okay? So, from A to B, nagre-release siya ng heat. So, kapag in-increase mo yung temperature, magba-backward yung ating process kasi bababa yung KEQ. So, ibig sabihin, pupunta from B to A, yung, or mag-favor sa A, yung equilibrium. Okay? Kasi, ini-increase mo yung heat. So, pag ini-increase mo yan, mag-shift yung equilibrium backward. So kapag dinidecrease mo naman, mag-shift yung equilibrium forward. Okay? Pag dinidecrease mo ang temperature ng isang exothermic system o yung system na nagre-release ng heat from A to B. Okay? So that's the effect of temperature. So now let's proceed to the effect of concentration sa equilibrium. So concentration changes, shift the equilibrium, but does not change the KEQ value. So temperature lang ang nakakapagpabago ng KEQ. Kapag concentration ang binago mo, the system will adjust to a new state. So magbabago lang yung mga amounts nila, mag-shift either forward or backward para mag-correspond yung mga concentrations niya doon sa KEQ. Okay? So in aqueous systems, the equilibrium may shift due to dilution. So kapag nag-add or re-remove ka ng water dun sa system, nagbabago pa rin yung ating concentrations or nag-shift pa rin yung equilibrium forward or backward kahit hindi kasama yung water sa KEQ. Okay? So, nadidilute kasi yung ating system. Ibig sabihin, nagbabago pa rin yung concentration kapag nag-add or remove ka ng solvent. Okay? So, nagkakaroon pa rin ng shifts in equilibrium. So, here we have components, concentration change, and equilibrium shift. So, ang analogy nito is like, for example, sa isang seesaw, okay? So, if the box is here, okay, tapos in-increase mo yung level nito, or let's say this side is a reactant side and this is the product side. So, kapag in-increase mo yung level nito or in-increase mo yung reactant side, yung box mo ay mag-move to the products. So, kapag ka naman sa ibang case wherein binaba mo naman yung side na to, okay, tapos nandito yung box, okay, reactants, products, mag-move yung box na yan further to the reactants. Or kung nandun siya sa product side, okay, kapag binaba mo yung level dun sa reactant side, mag-move yung box na yon sa reactant side. So, yung action ng ating box doon sa seesaw at saka yung ating pagtaas or pagbaba ng level ng seesaw, nagko-correspond siya doon sa action ng equilibrium or sa shift ng equilibrium kapag nag-i-increase tayo or nagde-decrease ng concentration. Okay? So, for example, okay, for reactants, kapag in-increase mo yung amount ng reactants, ibig sabihin, in-increase mo yung level dun sa reactant side, magfo-forward yung reaction. Ibig sabihin, yung box ay mag-move to the product side. So, ganun yung nangyayari. Okay? So, analogous lang yung action ng equilibrium dito doon sa action ng box doon sa seesaw kapag binabago mo yung sides. So, kapag ka-decrease, okay, magba-backward yung reaction. So, magpupunta yung equilibrium or may mag-favor siya doon sa reactant side. Okay? So, for products, okay, same pa rin yung gagawin natin. Kapag nag-i-increase yung products, magba-backward yung reaction kasi masyadong maraming products. Kapag naman nag-decrease yung concentration ng products, mag-move yung reaction or mag-shift yung equilibrium towards the product side. Okay? So, for the next parameter, okay, pressure changes shift the equilibrium. So, especially dun sa mga gas phase reactions or mga systems na may involved na gases dun sa equilibrium. But not the KEQ value. Kasi yung pressure, again, is related to the concentration of your species. So, na-derive natin yung relationship through the ideal gas equation. So, pareho lang din yung effect ng pressure doon sa effect ng ating concentration. Pero, let's look into the delta NG first. Okay? So, addition of inert gases, by the way, won't affect the equilibrium state. Kasi kahit mag-add ka ng inert gas, pareho pa rin yung magiging partial pressure ng inyong mga components doon sa equilibrium. Hindi nagbabago yung pressure nila. Although nagbabago yung pressure ng buong system, but not the partial pressure. So, hindi nagbabago, kumbaga, yung concentration ng mga species na involved doon sa equilibrium. So, wala siyang effect sa equilibrium. Okay? So, we now know the delta NG. So, the delta NG is the difference between the number of moles of products, tapos number of moles of gases sa products, saka number of moles of gases sa reactants. Okay? So, we have here the pressure change and yung effect niya sa equilibrium. So, kapag yung delta NG nyo ay greater than 0, ibig sabihin, mas maraming particles of gases sa products kaysa sa reactants, at nag-increase ka ng pressure, magba-backward yung reaction. Bakit? Kasi pag nag-increase yung pressure, yung system mo mag-a-adjust siya such that yung system mo ay mababawasan ng number of moles of gases kasi mas okay yon kapag sa equilibrium. Mataas yung pressure, so dapat fewer number of moles lang yung gas particles para makapag-adjust yung system mo. Okay? So kapag dinecrease mo yung pressure, mafe-favor naman yung side na mas maraming gas particles para ma-occupy niya yung system. So mag-forward yung reaction kapag positive yung delta Ng or kapag mas maraming gas particles sa products. So kapag less than 0 yung delta Ng, ibig sabihin mas maraming reactant particles or gas particles dun sa reactants, at in-increase mo yung pressure, magpo-forward yung reaction kasi mas konti yung particles ng gas sa product side. So mag-shift yung equilibrium forward. So pag dinecrease mo naman yung pressure, backward naman yung magiging shift ng equilibrium kasi mafe-favor yung mas maraming particles which is the reactants. Kaya negative yung ating delta G. Kapag walang delta Ng, ibig sabihin equal yung numbers of particles of gases doon sa products and reactants or walang gases na involved, okay? The increase or decrease in pressure won't affect the equilibrium or the system. Okay? So kahit itaas or ibaba yung pressure, since wala naman tayong delta Ng dun sa system, hindi niya maapektuhan yung system na yon or hindi niya mababago yung mga equilibrium pressures. Okay? So that's for some of the effects of some parameters sa ating equilibrium. Okay? So here we have some sample problems. Okay, so for the first one, the standard molar delta G of the following reaction at 300 Kelvin is 13,568.15 joules per mole nitrogen gas. So for the reaction, we have 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia gas. Okay, so ang una natin gagawin, let's calculate the Kp and the Kc of the reaction at 300 Kelvin. So calculate muna natin yung Kp. So we will use the standard delta G is equal to negative RT ln Kp. So kapag in-express nyo itong equation na to in terms of Kp, Kp is equal to E to the negative delta G naught over RT. Okay? So substituting the values, we have E to the negative of the delta G, which is 13,568.15 joules per mole over R, which is 8.314 times the temperature 300 Kelvin. So makakancel yung joules per mole and yung Kelvin, so magiging dimensionless yung exponent ng ating Euler's number. So if we calculate this, we will get 4.34 times 10 to the negative 3 for the Kp. Okay? Next, we will calculate the Kc of the reaction. So bago natin i-calculate yung Kc, calculate muna natin yung delta Ng. So the delta Ng is equal to the number of moles of gases or gas molecules in the product, which is 2, minus number of gases in the reactant side. So that's 3 plus 1, that's 4. So 3 moles of hydrogen plus 1 mole of nitrogen, 4 moles of gases in the reactant side. So that's 2 minus 4, negative 2 for the delta Ng. So after nyan, calculate natin yung Kc using this equation. Kp is equal to Kc times quantity RT raised to the delta Ng. So kapag ni-rearrange natin, we will get Kc is equal to Kp times quantity RT raised to the negative delta Ng. So substituting the values, we have the 4.34 times 10 to the negative 3 for the Kp. So dito sa quantity na RT, 8.314 times 300 Kelvin for R and P respectively. Tapos negative 2 yung ating delta Ng. So the negative of negative 2 is positive 2. So kapag kinalculate natin itong expression na to, we will get Kc is equal to 2.7 times 10 to the 4th power. Okay? So for the next part, calculate the equilibrium pressures if initially there are 2 moles of nitrogen gas and 2 moles of hydrogen gas in a 10-liter container at 300 Kelvin. So for the first step, let's calculate the initial pressures. So gagamitin natin yung ideal gas equation, PV is equal to nRT. So kapag ni-rearrange natin, we will get P is equal to nRT over V. So for the pressure of nitrogen, we have 2 moles of nitrogen gas times yung R natin, 0.08206. So ito yung gagamitin natin constant kasi kailangan natin ng pressure in ATM. So the temperature is 300 Kelvin over 10 liters, we will get 4.92 ATM for the nitrogen. So since pareho lang sila ng number of moles ng hydrogen, we will expect that they have the same pressures. So for the pressure of hydrogen gas, since 2 moles lang din siya, it is also 4.92 ATM in terms of its pressure. Okay? So after nun, calculate the equilibrium pressures using the initial change equilibrium table or the ICE table. So ano yung ICE table? So the ICE table shows you the initial, the change, and the equilibrium concentrations. So yung initials natin, wala pang ammonia na gas. So meron tayong 4.92 ATM ng nitrogen and hydrogen. So ang mangyayari kapag nag-shift yung equilibrium, mababawasan ng X moles si nitrogen. Since 3 times na mas marami yung hydrogen dun sa reaction kaysa sa nitrogen, given by the stoichiometric coefficients, so every time na mawawala ng X moles si nitrogen, magre-react siya sa 3X moles ng hydrogen to produce 2X moles ng ammonia. Kaya nadadagdagan ng plus 2x si ammonia. So we will expect that the reaction would shift forward kasi wala pang ammonia. Okay, kailangan magkaroon ng ammonia dun sa ating system at equilibrium. So at equilibrium, ang mangyayari, yung equilibrium pressures nila for nitrogen is 4.92 minus x. Yung x yung dami ng nag-react na nitrogen. Tapos 4.92 minus 3x. So 3x yung hydrogen gas na nag-react. So magkakaroon na tayo ng 2x ATM ng ating ammonia. Okay? So to be able to calculate the equilibrium pressures, we need to write the Kp, or the equilibrium constant, in terms of the pressure. So Kp is equal to the square of the pressure of ammonia over the pressure of nitrogen times the cube of the pressure of hydrogen. So that's equal to 2x squared, so quantity 2x squared, over 4.92 minus x times 4.92 minus 3x cube. Okay, so ito yung mga equilibrium pressures nila. Okay, tapos i-equate natin siya sa Kp, which is 4.34 times 10 to the negative 3. So using the solver function on your calculator, you can actually set up this equation sa calculator nyo, tapos you can just solve for x directly. So solving the equation, we have x is equal to 0.462 atmospheres. So for the pressure of ammonia, that's 2x. So i-multiply nyo lang sa 2 yung x, or yung 0.462, you will get 0.924 atmospheres. So for the pressure of hydrogen, that's 4.92 minus 3x, you'll get 3.534 atmospheres. For the pressure of nitrogen, that's 4.92 minus x, so that's 4.458 atmospheres. So ito na yung mga equilibrium pressures ng inyong mga gases. Okay? So for the next part, calculate the equilibrium pressures if initially there are 2 moles of nitrogen, hydrogen, and ammonia in a 10-liter container at 300 Kelvin. Okay, so same pa rin yung ating reaction. 1 mole of nitrogen plus 3 moles of hydrogen produces 2 moles of ammonia, and it is a reversible reaction. So pwedeng to the product side, pwedeng to the reactant side. Okay, this is the Kp of the reaction. Ito yung na-calculate natin kanina. Okay, so ang unang step, calculate the pressure of each gas and then calculate the reaction quotient Q. So since pare-pareho lang ng number of moles yung gases natin initially, pare-pareho lang din yung kanilang partial pressures. So pare-parehong 4.92 atm yung kanilang pressures initially. Okay? So, then, pwede na natin i-calculate yung reaction quotient Q. So, yung expression ng Q at KEQ pareho lang. Pero yung Q, pwede natin i-calculate yung initial niyang reaction quotient para malaman natin yung difference niya sa KEQ. So, let's remember that if Q is greater than KEQ, magba-backward yung reaction natin at equilibrium. So, to approach equilibrium, I mean. Okay? So, kapag less than KEQ naman yung Q, magpo-forward yung reaction natin para mag-approach dun sa value ng KEQ. So, calculating using the initial values of the pressure, we will get Q is equal to 4.131 times 10 to the negative 2. So that's greater than 4.34 times 10 to the negative 3. So mas malaki yung Q kaysa sa KEQ. Okay? So since Q is greater than KEQ, we will expect that the equilibrium is shifted backwards. So ibig sabihin, mababawasan yung ating ammonia at madadagdagan yung hydrogen and nitrogen natin. Okay? So now let's use the ice table. So ngayon, ina-expect na natin na mababawasan si ammonia at madadagdagan si hydrogen and nitrogen. So initially, meron silang tig 4.92 atmospheres. So upon change, mababawasan ng 2x atmospheres si ammonia at madadagdagan ng 3x atmospheres si hydrogen at x atmospheres si nitrogen. So at equilibrium, meron ng 4.92 plus x atmospheres ng nitrogen, meron ng 4.92 plus 3x atmospheres ng hydrogen at may 4.92 minus 2x atmospheres ng ammonia. Okay? So, isa-set up na natin yung equation. So, Kp is equal to 4.34 times 10 to the negative 3 is equal to yung equilibrium pressure ni ammonia. That's 4.92 minus 2x squared kasi this is P NH3 squared over pressure ni N2, which is 4.92 plus x times the pressure of hydrogen cube. So, that's 4.92 plus 3x cube. Okay? So, solving for the equation, we will get x is equal to 0.757 atmospheres. So, for the pressure of nitrogen, that's 4.92 plus x, we get 5.677 atmospheres. For the hydrogen, that's 4.92 plus 3x, okay? So, that's 7.191 atmospheres. So, for ammonia, that's 4.92 minus 2x, we get 3.406 atmospheres. So, ginagawa natin yung technique na to para hindi mag-negative yung mga solutions natin ng x, okay? Hindi tayo malito doon sa ating equilibrium calculation. Kasi kapag ine-expect na natin kung saan mag-shift yung equilibrium through the Q, alam na natin kung ano yung subtraction at addition na mangyayari upon change. Okay? Alam na natin kung alin ang madadagdagan at alin ang mababawasan. Reactants ba or yung products. Okay? So for this next part, let's calculate the new equilibrium pressures if the container is compressed to 5 liters at 300 K constant temperature after attaining the equilibrium in C. So nakalculate na natin yung mga equilibrium pressures kanina dun sa C. So dito, after reaching the equilibrium, i-compress natin yung container. Gagawin natin siyang 5 liters. So ano kayang mangyayari? So first, calculate natin yung mga bagong pressures using the Boyle's law. So Boyle's law is P1V1 is equal to P2V2. So to calculate for the new pressure, P2 is equal to P1V1 over V2. Okay? So for the pressure of nitrogen, that's 5.677. That's the equilibrium pressure kanina sa C. Times 10 liters. Yan yung container kanina. Okay? Tapos kinompress natin to 5 liters. Okay? So that's 11.354 atmospheres for nitrogen. So doing the same for hydrogen, we will get 14.382 atmospheres. So for ammonia, we will get 6.812 atmospheres. So pare-pareho lang yung changes ng volume nila kasi nasa iisang container lang sila. Okay? So now, calculate natin yung reaction quotient. So calculate the reaction quotient and compare to KEQ. So let's calculate the reaction quotient. So pressure of ammonia squared over the pressure of nitrogen times the pressure of hydrogen cubed. So 6.812 atmospheres squared over 11.354 times 14.382 atmospheres cube. So makukuha natin ay 1.374 times 10 to the negative 3, okay, for the reaction quotient. That's less than 4.34 times 10 to the negative 3. So the Q is now less than KEQ. So the equilibrium shifts forward. So bakit kaya? So makikita natin yung reaction natin kanina. Plus 3H2, a gas, produces 2 moles of ammonia. Okay? So since nag-increase tayo ng pressure dahil bumaba yung volume, nag-favor yung production ng ammonia. Bakit? Kasi mas konti yung number of particles sa product side. So magpo-forward yung equilibrium natin upon increase in pressure or decrease in volume. Okay? So for the next step, let's solve for the equilibrium pressures using the ice table. So since Q is less than KEQ kanina, okay, so in-expect na natin na magpo-forward yung ating reaction. So ma-favor yung production ng ammonia. So from the equilibrium pressures kanina, okay, magbabago ulit yung kanilang pressure since mababawasan yung amounts or yung pressures ni nitrogen and hydrogen at madadagdagan yung pressure ni ammonia. So at equilibrium, nitrogen is 11.354 minus X atmospheres, tapos si hydrogen ay 14.382 minus 3X atmospheres, tapos si ammonia ay 6.812 plus 2X atmospheres. So substituting to the Kp expression, that's 4.34 times 10 to the negative 3 is equal to again, Pn2 squared, so that's 6.812 plus 2x squared over the P and N2, okay, that's 11.354 minus x, tapos PH2 cube, that's 14.382 minus 3x cube. Okay, so solving for the equation, okay, or solving for x, okay, we will get x is equal to 0.881 atmospheres. So for the pressure of nitrogen, that's 11.354 minus x, that's 10.473 atmospheres. So for hydrogen, that's 14.382 minus 3x, 11.739 atmospheres. So for ammonia, that's 6.812 plus 2x, 8.574 atmospheres. So nadagdagan yung amount ni ammonia dahil nag-increase yung pressure due to the decrease in the volume. Okay? So for the next problem, let's consider this reaction. So acetic acid in aqueous solution reacts with water as the solvent to produce the acetate anion plus the hydronium cation. Okay? So the KEQ for this reaction is 1.75 times 10 to the negative 5. So 1, calculate the equilibrium concentrations if the system initially contains 0.10 molar acetic acid. So this KEQ is KC. Automatic yan kapag ka-aqueous solution. Okay? Hindi mo ma-determine ang pressure ng mga aqueous solution. So let's assume that the 1.75 times 10 to the negative 5 is the equilibrium constant in terms of concentration. Okay? So using the ice table, we have 0.10 molar. So hindi natin sinasama yung water sa initial. So wala pang acetate and hydronium at initial conditions. So of course, mag-shift yung equilibrium forward. So mababawasan ng x moles or x molar si acetic acid at padadagdagan ng x molar si acetate and hydronium. So the equilibrium concentrations are so 0.10 molar minus x for acetic acid, x molars for acetate, and x molars for your hydronium. Okay, so this is the KEQ. So the KEQ is the concentration of acetate times the concentration of the hydronium cation over the concentration of the acetic acid. So that's x, okay, times x over 0.1 molar minus x. So equate natin siya sa 1.75 times 10 to the negative 5, which is our KEQ. So solving the equation, we will get x is equal to the concentration of the acetate and equal to the concentration of the hydronium. That's 1.31 times 10 to the negative 3 molar. So pareho lang na X yung concentration ni acetate and hydronium na 1.31 times 10 to the negative 3 molar. So for the acetic acid concentration, that's 0.1 minus X. So that's 0.0987 molar. Okay? So for this next part, tingnan natin yung effect ng concentration or tingnan natin yung effect ng addition or removal ng water. Okay? So for number 2, calculate the new equilibrium concentrations if the volume of water is doubled. Okay? So magdadagdag tayo ng water doon sa ating system after the equilibrium is obtained. So assume natin na nasa equilibrium na yung acetic acid solution natin, tapos mag-a-add tayo ng water. Ido-double natin yung volume ng water. Okay? So if the amount of solvent is doubled, the concentrations are halved. Okay? So, nadoble yung ating volume ng solvent, mangangalahati ngayon yung concentrations ng ating mga solutes. So, let's just divide the concentrations by 2. So, for the equilibrium concentration of the acetic acid, okay, 0.0987, madidivide sa 2 yon, magiging 0.0494 molar. Yan yung bagong initial concentration niya. Sa acetate, okay, 1.31 times 10 to the negative 3 molar divided by 2, that's 6.55 times 10 to the negative 4 molar. So, that's the same as the concentration of your hydronium cation. Okay? So, yan na yung mga bago nilang initial concentrations. So, now, let's calculate the reaction quotient. Okay? So, for Q, that's the concentration of your acetate times concentration of hydronium over the concentration of your acetic acid. So, that's 6.55 times 10 to the negative 4 molar squared, kasi pareho lang na concentration si acetate and hydronium, over the 0.0494 molar concentration of your acetic acid. So makikita nyo na that's 8.685 times 10 to the negative 6. Okay? That's less than 1.75 times 10 to the negative 5, which is the KEQ of the acetic acid dissociation. So since Q is less than KEQ, the equilibrium shifts forward. So mapapansin nyo dun sa reaction, okay? So acetic acid plus water produces acetate plus hydronium. So nag-add tayo ng mas maraming water. So we will expect that the equilibrium will proceed forward or mag-shift to the right side yung ating equilibrium. Okay? So that's for the explanation of this reaction quotient. Okay? So now let's use the ice table. Okay? So same pa rin yung reaction. Acetic acid plus water produces acetate anion plus hydronium ion in solution. So for the equilibrium concentrations na nakuha natin from number 1, we have 0.0987 molar for acetic acid and 1.31 times 10 to the negative 3 molar for acetate and the hydronium cation. So after doubling the volume or dinagdagan natin yung water, okay? So ito na yung bagong concentrations. So 0.0494 molar for acetic acid, 6.55 times 10 to the negative 4 molar for acetate and the hydronium. So since nakuha natin na yung reaction quotient ay less than the KEQ, we will expect na madadagdagan yung amount or concentration ng acetate and hydronium and mababawasan yung concentration ng acetic acid. So, for the equilibrium concentrations, 0.0494 molar minus X, yan yung sa acetic acid. So, 6.55 times 10 to the negative 4 molar plus X naman sa acetate and the hydronium. So, isa-substitute lang natin yung mga values na to dito sa ating KEQ expression. And we know that the KEQ is 1.75 times 10 to the negative 5. So, this is equal, okay, to 6.55 times 10 to the negative 4 molar plus X squared, kasi dalawa silang 6.55 times 10 to the negative 4 over the 0.0494 minus X for the acetic acid equilibrium concentration. So, solving the equation, we will get X is equal to 2.722 times 10 to the negative 4 molar. So, solving for the concentration of acetate and hydronium, we will get 9.272 times 10 to the negative 4. For the acetic acid concentration, we will get 0.04913 molar acetic acid. So, this is my discussion on the concepts of chemical equilibrium and some examples of the calculations in equilibrium constants and systems in equilibrium. Okay? So, sa susunod na discussion, I'll discuss specific types of equilibrium, acid-base, solubility, and metal complex equilibria. So, see you next video.